This is a short addendum to the Unified Framework report I published back in May. That report validated the quantum context frame selector, the circuit that routes conversational operating mode across 4 hardware backends with 83 to 96% consistency. That finding still holds. Nothing here changes it. But there's a second, related circuit in the same production file, quantumrouter.py, called quantum select fragments. It decides which memory fragments get loaded into an agent's context based on relevance scores. Unlike the frame selector, this one was never validated with the same rigor. And when I reviewed it during some unrelated infrastructure work this month, I found a structural defect in it. This addendum documents that defect, the test I built to confirm it empirically, the results on both simulated and real quantum hardware, and the 2-stage correction, including a second, subtler bug that only showed up after the first fix. Consistent with how I've approached this whole framework, showing the failure mode alongside the correction is more honest than only showing the parts that worked. Here's the original circuit. Each qubit gets put into equal superposition with a Hadamard gate. That's the H. Then a phase rotation, RZ, gets applied, scaled by the fragment's relevance score. Probability of measuring a 0 versus a 1 once that qubit is already in equal superposition. So no matter what relevance, here's the problem. RZ is a phase gate. It rotates the qubit's phase around the z-axis, but it does not change the core got fed into it. The measurement odds stayed locked at 50-50. The relevance scores were being encoded into the circuit, but there was no mathematical path for them to actually influence which fragments got selected. This is different from the frame selector, which correctly uses RY gates, gates that genuinely rotate probability as a function of the input angle. 2 different circuits, 2 different gate types, and only one of them was built correctly. I didn't want to just rely on the analytical argument, so I built 2 tests to confirm this empirically. The same standard I've held every other claim in this framework to. Test 1 was a single qubit sweep. Feed the relevance score from 0.0 to 1.0 in steps of 0.1, run 1,000 shots at each point. If relevance genuinely mattered, the probability of measuring a 1 should trend clearly across that sweep. If it didn't, that probability should stay flat around 50%, no matter the score. Test 2 was a full pipeline ablation. I ran the actual fragment selection function on a fixed 6-fragment set, the same one from the original demo, once with the real relevance scores, and then 20 more times with those same score values shuffled randomly across the fragments. If relevance was driving selection, the real run should look distinguishable from the shuffled runs. If it wasn't, the shuffled runs should scatter widely instead of converging back toward the real result. On the local simulator, Test 1's spread across the whole sweep was just 0.039, basically flat. Test 2's shuffled runs reproduced the real selection in only 1 out of 20 tries and produced 20 different unique outcomes out of 20 shuffles. Both tests confirmed no effect Mies. Then I took it to real hardware, IQM Garnet, through AWS Breakit. Test 1 spread on real qubits, 0.54. Same result. No effect confirmed independently on actual quantum hardware, not just simulation. On the hardware run, Test 2 held up the same way. Real selection was reproduced by random shuffles 0 out of 20 times, but 13 of those 20 shuffles still produced unique selection sets. That's a full hardware confirmation at a real cost of about $57.60, rather than resting this finding on simulation alone. So the obvious fix is to swap RZ for RY, matching the gate the frame selector already used correctly. I tested that first before adopting it. Across every fragment set I tested, whether the relevant scores were real or randomly shuffled made no detectable difference in which fragments got picked. The circuit's output was consistent with pure chance, not with relevance-weighted selection. So the obvious fix is to swap RZ for RY, matching the gate the frame selector already used correctly. I tested that first before adopting it, and here's the catch. It does produce a measurable effect, but the wrong one. With H applied first, the actual probability function becomes 1 plus sine score pi, or 2. That function peaks at a score of 0.5 and returns to roughly 50% at both score equals 0.0 and score equals 1.0, which means a maximally relevant fragment, and a completely irrelevant fragment would get almost the same selection probability, while a mediocre, middling relevance fragment would get selected almost every time. Backwards from what you'd want, and I verified that directly before shipping anything. Two things are worth naming plainly here. First, the obvious one. A production system was making memory fragment selection decisions that had no relationship to the relevance scores it was supposedly weighing for an unknown period of time without any error or warning. The failure was silent by nature. The circuit ran successfully and returned a plausible-looking result every time. Nothing about its output distinguished a working, relevance-weighted selection from a completely non-functional one, which is exactly why this required an empirical ablation test to catch, not just ordinary operation or a code review. Second, the less obvious one. The first attempted fix was also wrong, and it would have shipped as correct if it hadn't been tested with that same rigor. A gate swap that does something is not the same as a gate swap that does the intended thing. Verifying a fix requires the same empirical standard as identifying the original defect. Confirming an effect exists is necessary, but it's not sufficient. You have to check the shape of that effect too. Status right now: quantum select fragments has been corrected and verified at both the unit level, isolated gate behavior, and the integration level, full 6-fragment selection across 5 trials. Production deployment and a live traffic confirmation pass are the next steps. Following the same validate before trust standard, this whole framework has been built on. And to be clear, the frame selector itself, Quantum Select Frame, required no changes and remains validated exactly as reported in the May 2026 framework document. If you like this video, check out some of my other experiments and findings on my channel, and also check out my blog. I'll leave the link in the comments. As always, stay safe and use AI responsibly. See you in the next video.